Wearing windproof jackets and snow boots, a group of researchers depart on a cruise from Tromsø, Norway. Snow falls in thick layers. Temperatures steady around -15 degrees Celsius. The cruise moves up north along the 78th latitude, where the resident population steeply thins out. The twinkling lights of shoreline towns are replaced by relatively uninterrupted bouts of nighttime darkness. As the ship glides deeper into the Arctic Circle, the researchers release a special device into the icy waters below. Named the Manta Troll for its unique metal wings and broad mouth resembling a manta ray, the vehicle drags along a thin mesh net and picks up tiny samples on the surface of the ocean. From the collected materials, you might expect to find tiny ice chips swirling at the surface, or even a colony of microscopic plankton. The researchers indeed identified both, but also found something much more out of the ordinary. Under a powerful stereo microscope, they saw alarming amounts of microplastics, or tiny plastic particles undetected by the naked eye. I'm your host, Michelle Liu. Welcome to Earthtech Radio, your gateway to exploring how technology can radically transform our environmental future. While these tiny but harmful particles might begin from a discarded soda can, construction site runoff, or factory dye components, microplastics have migrated towards the remotest corners of the world, and at the same time, infiltrated our bodies. The story of microplastics discovery in the Arctic is only one piece of the puzzle. In 2018, microplastics were found in the Mariana Trench, also known as the deepest oceanic trench on Earth. UNM researchers found that plastic accumulation in the human brain has increased 50% in just the last 8 years. Tackling microplastic pollution is a challenging task. Microplastic particles are virtually undetectable, collecting in our everyday spaces and secluded corners of nature at alarming speeds. This exact quality may explain why it took scientists so long to fully recognize the scope of microplastic pollution, and why they are still searching for solutions in the present. In 2016, a team of researchers at the Kyoto Institute of Technology gathered around a microscope, surveying a surprise discovery. Their experiment began at a plastic bottle recycling site at Sakai City. Surrounded by piles of abandoned packaging supplies and colorful textile scraps, the team collected samples of wastewater and sediment contaminated with PET plastic. Originally, the researchers looked for organisms that could survive on the plastic material. Soon enough, they began to notice irregularities. Parts of a thin PET film used to support microorganisms began to degrade, with small holes appearing on the surface. Upon closer investigation, the scientists discovered a small rod-shaped bacteria, Ideonella sakaiensis. They watched as the bacterium broke down PET into its basic building blocks, terephthalic acid and ethylene glycol. Other microbes living in the same environment used those components for food. As they digested them, 75% of the plastic carbon ended up as carbon dioxide. The discovery of Ideonella sakaiensis, one of the only microorganisms that can use plastic as a primary energy source, spurred excitement from the environmental engineering world. The scientists behind this breakthrough further genetically modified the PETase enzyme found in this bacteria, combining it with a different enzyme, metase, to break down plastic at faster speeds. The team of researchers at KIT are looking towards potential applications of the bioengineered bacteria. They're not alone. Joined by environmental engineers around the globe, practical use of plastic-eating bacteria is an emergent pocket of study. as the Pacific garbage patch expands every year from the current 2.41 million tons of trash, all the while microplastics enter the human lung and bloodstream. Finding a sustainable means of microplastic breakdown is more important than ever. At the University of Sao Paulo, scientists have taken a different approach to fixing microplastics. A team of researchers observed how mussels cling tightly to surfaces, a special property that makes them so hard to remove from rocks and ship hulls. Both humans and mussels have dopamine, a neurotransmitter and hormone. Mussels are able to achieve this tight adhesion because of dopamine-containing proteins found within their tissue. Based on this natural stencil, scientists created polydopamine, a synthetic polymer. The USB researchers used polydopamine to functionalize nanoparticles that cling to the surface of microplastics. These tiny agents are able to identify microplastics at greater efficiency and accuracy rate than normal filtration techniques. Afterwards, the scientists apply a magnetic field, which removes the tagged microplastics from the rest of the water. So while microplastics are a problem that permeates spaces from remote rainforests to packaged drinking water, there's a growing momentum to understand its impact. As our researchers in the Arctic Circle make the slow journey back to Tromsø, they carry precious research that shows the far reach of microplastics, bringing the issue to the attention of the scientific community and public alike. International researchers are synthesizing new methods to sort and eradicate microplastics before they interfere even more with our lives and the greater environment. The microplastics fix doesn't lie in a single science. Rather, our collective focus and curiosity can help filter these harmful materials out of our lives for good. Thank you for listening to today's episode of Earthtech Radio. We truly appreciate listeners like you, who are passionate about the intersection of sustainability and innovation. Join us next time for an episode on the story of the forever chemical Teflon.